Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem, minimum difficulty of a job schedule. Kind of a confusing problem, so I'm really going to focus on the example that we have here. So the idea is that we have a bunch of jobs and we're given the difficulty of each job in this input array. We're also given a number of days. So what that means is we want to split up this list into two parts for this example because D is 2. So we want to do some of these jobs on day 1 and the rest of the jobs on day 2. Of course, if D was equal to 3, then we do it like split them up into 3 different ways. And we can choose how we want to split them up, but on every single day, each one of these has to be non-empty. So we have to do at least one job on every single day. We can't just say, okay, do this on day 1, day 2, and on day 3, do nothing. And we have to make sure that we include all of the jobs in total. We can't miss any of these jobs. In addition, we have to do the jobs sequentially. So it's not like I can say, okay, this job and this job are going to be on day 1, these jobs are going to be on day 2, and these jobs are going to be on day 3. We can't do that. We have to do them continuously. The problem description tells you the same thing, just in more confusing wording. Now, once we have done that, let's say we split it up like this and this. We want to calculate the total difficulty of doing that. And it's not by just taking the summation of all the difficulties. What we actually do is we take the maximum difficulty on day 1, basically the max of this subarray, it's 6. And we take the max of this subarray on day 2, it's 3. So we take those up and add them together. That's the total difficulty of splitting it up this way. Now, obviously that's not the result. So what do we want to do for the result? Well, we want to find a way to split these up such that the result is minimized. So the solution to that would be to do 5 of these tasks on day 1, because then the maximum is still 6 from there. And then on day 2, do 1. And then we add those together, and then we get 7, which is the correct output. Okay, so the first idea that you might have, and the first idea I had, was let's just try every possibility, right? Let's try to break it up every possible way. How can we even do that? Is that even feasible? And if it is, can we then add a little bit of caching to that solution? Let's try to find out. So we don't have that traditional choice of whether we want to include this or not include it. The choice that we do have, though, is on 6, do we want to consider this the end of day 1? Or do we want to have 6 and it's not the end of day 1? And then we have another choice. We get to 5. Do we want to consider this the end of day 1? Or do we want to have 5 and not consider it the end of day 1? And here we'd continue as well. If this is the end of day 1, then we'll get to 5 and say maybe this is the end of day 2. Now, of course, this shows us what one of our base cases is going to be. What happens if we stop too early? We have additional days left, but one of the parameters that we're keeping track of as we iterate over this array is, of course, going to be index I. That tells us which job that we're currently at. But a second one, of course, is going to be D, the number of days that we have remaining. Here, initially, it's 2. By the time we end this day, it's going to be 1. And then by the time we end this day afterwards, it's going to be 0. If we ended all the days, we expect I to be equal to the end of the array, but it's not. So here we return. This is not a valid way of doing this. So when we return, we're going to return infinity. So basically to indicate that this was not a valid way. This does not count as a solution. So that's showing us one of the base cases, basically the invalid one. Just to kind of continue with this, here we might get to 5 and not consider it the end of the day. Now let me just kind of fast forward and skip to when we get to 4, we get to 3, then we get to 2, and we want to consider 2 to be the end of the day, and then we get to 1, and we want 1 to also be considered the end of the day. So we have a day that looks like this, and we have a day that looks like this. We know this is the correct solution. I'm just not drawing out the rest of the tree. But from here, how do we return a result of 7? We know that from this group, the maximum was 6. We know that from this group, the maximum was 1. But how do we end up returning that? Well, I think one possible way is to have a third parameter. We have I, we have the number of days remaining, and I propose we have another one called the current maximum. It's not the maximum from the entire array, it's the maximum for the current day that we're at. So initially, when we get here, okay, we see a 6. We're going to set that to the current max. Now we see a 5. Current max is still 6. 4, current max is still 6. 3 and 2, current max is still 6. But when we say this is the end of the day, then when we call this recursively, we're going to say, okay, the result now is going to be 6 plus this subproblem. There might be more values remaining, but the result is going to be 6 plus whatever the current max from the second day happens to be, which we know ends up being 1. So then we get the result of 6 plus 1. Once we get to the subproblem, of course, at that point, we are going to reset the current maximum. We're going to reset it from being 6, which it originally was, but now we're going to probably reset it back to some small value, probably something like 0 or -1, because I think all the job difficulties are going to be greater than or equal to 0. And then immediately when we get here, we're going to end up setting the current max from -1 to being +1. And since that's the base case, this is the case where we ended up reaching days are equal to 0 and I is out of bounds. I has gone through every value in the input. That is the valid base case where we would return 0. And then from this call, we would return 1. And then from this call, we would return 6. So we add those together and we would get the result of 7. So that's how we can solve this problem. At least this is the brute force way. But when you notice that we have 3 parameters, we know this is when we can add caching to the problem. We can use the parameters to prevent repeated work. So how many combinations of input parameters can there be for this? Well, I can have a possible value of the length of this input array. So far the time complexity is big O of n. Second, D can have a possible value for whatever D happens to be. So n times D is the time complexity so far. What about current maximum? What are the possible values it can have? Well, at any given point in time, current max could be any of the previous values. Like if we had started the day here, current max could be 4. If we started the day here, current max could be 3, etc., etc. So this, in the worst case, could also be n. So the overall time complexity, if we add caching, is going to be n squared times d. And the memory complexity is going to be the same. And this actually is enough to pass on Leetcode. So let's code this up. Now, one thing I actually didn't mention is that it's possible for the number of days to actually be greater than the length of this array. That would make it invalid. We can't split this array into this many ways if there's not enough jobs. So they tell us in that case to return -1. So we can handle that pretty easily just by hard coding a if statement here. So if the length of job difficulty is less than D, then just return -1 as the default. But continuing, let's do our recursive backtracking or DFS, whatever you want to call it, and then we'll add caching to that afterwards. So we know we keep track of the current index, we keep track of the number of days left, and we keep track of what the current maximum in the current day happens to be. So the way we're going to call this is by returning DFS starting at index 0, starting with this many days, and current max, I think you can probably set it to 0, but I'll set it to -1 just to indicate that so far it's invalid. Now, starting with the base cases, we know that there's one base case where I reaches the end of the array, the end of the job difficulty array. Now, in that case, we want to return 0 if and only if D is also equal to 0. But if it's not, then we can return a really big value to indicate that this is invalid, which is going to be infinity in our case. The reason we're returning 0 rather than 1 is because think about it in terms of this subproblem. We have nothing left in the array and we have no days remaining. So from that subproblem, of course, it's not going to take us any work or difficulty or whatever, so we return 0 from there. But from the other recursive calls, you're going to see we do return non-zero values. Now, the other base case, though, is what if we haven't reached the end of the array, but it's still true that D is somehow equal to 0? That is, again, where we return infinity, because it's not possible for us to do that. We don't want any jobs remaining, so we return infinity here as well. Now, let's go into the recursive case, but before we actually do that, we know we're keeping track of what the current maximum happens to be. We might need to update it. That's exactly what we're gonna do. We're gonna set it to max of itself and the current job. So job difficulty at index I. This will make it so that no matter what, on the first iteration of the DFS, current max will be -1, and we'll set it to whatever the first job happens to be. So it won't stay -1 for very long. Next, let's do the recursive case. There are two cases. One where we continue with the day. The second is where we end the current day. How are we going to call this recursively for each case? Well, one is going to be easier. So let's start with it. Continuing the day, we're just going to go to I+1. The number of days is going to stay the same. We haven't ended any day yet. And the current max is just going to be whatever it happens to be right now. The other case where we end the current day is a bit more interesting. We do go to I+1, but if we're ending the day, we should probably decrement the number of days. And lastly, what is the current maximum going to be? We just took the current maximum. This is the current maximum of the current day. But if we're ending that day, current maximum should be reset. And we're going to reset it back to -1. Or you could probably also do 0, I think. So this is the two cases, and we know among these two, we're trying to minimize the difficulty, like it says up above. So we should take the minimum of these two function calls. So I'm going to do exactly that, and don't forget to put a comma right there. I'm going to assign this to a result variable, which is what we're going to end up returning. So while this solution is correct, it's not as efficient as it can be. So to add caching to this solution, we're going to first create a hash map cache. It's usually easier than doing like a 2D or 3D array. Before we return this result, we're going to throw it in the cache like this, using the parameters as a key. ID and current max is equal to result. And if we ever see this result has already been computed like this, if it's in the cache as a key, then we can return it. I'm just going to copy and paste it here. If you're not familiar with this type of caching, I would definitely recommend looking at some easier videos of mine. Probably Leetcode 70 is a good way to learn about caching. Or you can also check out like the courses that I've made on Leetcode.io. But let's go ahead and run this to make sure that it works. And of course, it looks like we had a mistake, which is a typo. And there's actually one last thing I forgot about. I said that we aren't always going to return 0, and this is the part where we don't want to. If we end the current day, we have the maximum of that current day. So to the result of like this subproblem, we want to add that current maximum. So just like this, we're going to add current max. We know that's the maximum of the current day, and then we're going to solve the rest of the subproblem for the remaining number of days. Now I'm going to run this and hopefully it will work. As you can see on the left, yes, it does. The runtime isn't as efficient as it can be because actually there is a way we can use dynamic programming, I think, in addition to a monotonic stack to get the time complexity from being n squared times d down to just big O of n times d, but I think I will leave that as an exercise for the reader. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.